part A. Okay, slope fields. I can do slope fields. I got this. I got slope fields. Alright, just draw it out, map the slopes, make sure you plug things in the right places. I can do slope fields. Alright. Check. A done. I got this.
I know this. I can do this. Oh, I wish I was somewhere else.
A slope field is a graphical representation of the solution to a differential equation.
How do you make one?
By taking each point indicated and plugging in its x and y coordinates to the differential equation to find the slope, which you then mark on the graph with a small line segment.
Okay, part B. Implicit differentiation, just gotta separate it. Not a big deal. Done a bunch of these. Get the x's on one side, the y's on one side. Okay, this is odd. It doesn't really want to separate. It's okay, I'll get it. Sometimes it takes me a minute, I'll get it. Is this really not going to separate? Seriously, what? I can't waste this much time. Why is this not separating? There's nothing I can do short of making up algebra right now. Why will this not separate? There's no way for me to get the y's and the x's on separate sides. It's usually multiplication. Why will this not separate? 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 Okay, this is so frustrating. I know how to take the derivative. You just take the derivative of the top over the derivative of the whole thing over the derivative bottom part from the other thing. Oh, okay, I'll write that, see if they give me any points. Ugh, but I have to choose concavity. Well, I guess down. Down. It's definitely down. Just because that's the way I feel right now.
When taking the derivative of a differential equation, remember to treat y as a function. You can use a second derivative to determine concavity, which refers to the direction in which the graph bends.
Okay, part B. Part A went pretty well, so hopefully part B will be okay too. It's asking for the second derivative. So they've given us the first derivative, so all we need to do is find the derivative of that. And it's in respect to x. So the derivative of 2x is 2, and then the one of y is dy dx. And then we just plug in 2x minus y for dy dx, because that's what they give us. And that gives us the second derivative. Looking good so far. Okay. Now, concavity in quadrant 2. So everything in quadrant 2. X will always be negative, and y will always be positive. So if we just plug that into the second derivative, it's going to go positive, and then a negative minus a negative is also positive, and then a y is also positive. So all solutions will always be positive to the second derivative in quadrant 2. So if it's all positive, that means it's concave up, right? Yeah, that sounds pretty good. Okay, so all solutions in quadrant 2 will be concave up. Perfect. Section B, check. Alright, okay, moving on, part C. Hopefully they're not connected. I got this. I just gotta plug it in. They gave me the initial condition, I just gotta plug it in to the formula that I didn't know how to write because it's not separable. Why is it not separable? Okay, I'll separate it one more time. It's gotta be separable, right? If they put it on this test, it has to be separable. They can't make one that's not separable. That's not how it works. Am I just so freaked out that I cannot figure out how to do this? Why can I not figure out how to do this? I know how to do algebra. I know how to separate a differential equation. Why can I not figure out how to do this? Okay, whatever. It's a minimum. But maybe it's a maximum. Maybe I can make it look like both? Perfect. Perfect. Maybe I'll get a nice grader. Oh my goodness, this is so frustrating. I studied for this. Okay, part C. So it's giving us an initial condition, and they want us to find if it has a minimum, a maximum, or neither. So since we're given the derivative, and the critical point has to equal 0 at the derivative, we can just plug the critical point into the derivative. So if we plug in 2, 3 into dy dx, and then we solve, we should get 1. And 1 is not 0, and so this is not a critical point. So if it's not a critical point, it's neither. It's not a maximum or a minimum. Perfect. Part C, check.
Okay, last part. Maybe I'll have a breakthrough that helps me backtrack into all the rest of the problems. This is just a linear formula. This cannot be that difficult. This is like 6th grade algebra. Okay, got the constants. Wrote down what I know. That's got to be worth a couple points, right? Maybe half? Half for writing down what I know? Okay. Shoot. Back to the whole separating thing again. Maybe there's a different way that I can just plug this in. So I can just plug in the constants. Maybe the constants from the last problem? Maybe if I just get rid of the dy dx. Integrate, maybe? Why is this not working? Ugh, I'm getting this whole thing wrong. I don't know what I'm doing. But I know how to do this kind of problem. I studied this. I thought I studied this. Okay, whatever. Ugh, I wish this were a related rates problem. I watched like 8 Khan Academies on related rates. Why is this not a related rates problem? And the whole time, the guy was just shading cones, and I was like, yeah, I totally get this. Like, I totally get this. And now I'm really good at shading cones, but I can't figure out how to separate a differential equation. Maybe I'll get a cool grader that'll just give me points for pictures or effort or I don't know.
And finally, part D. Hopefully it won't go downhill from here. So it gave us the solution as y equals mx plus b, which is linear. Since it's linear, if we take the second derivative, we should get 0. So let's set it up. The second derivative from part A equals 2 minus dy dx, which is also equal to m, is equal to 0. If we solve this, we should get m equals 2. Okay, halfway there. So m, or dy dx, is given as 2x minus y, and it equals 2. If we solve for y, we get y equals 2x minus 2, which is the same form as mx plus b. Therefore, b equals negative 2.
Yay! Part D, check. Woo! I did it!
Put your pencils down.